In this example, we've got a vector field, and we've got a curve, and we need to find the circulation of the vector field around the curve in a particular direction. So if we look at this curve, we're in 3 dimensions, so we've got x, y, and z, but it tells us that the curve is a square in the xy plane. Particularly, it's a square bounded by the lines x equals 1 and negative 1, so that would make a line back here and a line up here, and the lines y equals 1 and negative 1. That makes a line here and a line there. So there's the curve created by the boundaries from those 2 infinite lines. So this is our curve C, and we need to go around this curve counterclockwise as viewed from above. You can see if you look down from the z-axis, then this is the direction that would be counterclockwise. So we need to do that circulation integral, but to do it directly, we would have to parameterize the curve over one bit, find the flow along that bit, and then parameterize this next piece, find the flow along this piece, parameterize the next piece, find the flow along that piece, parameterize the 4th piece, find the flow along that piece. So it's going to require 4 parameterizations and 4 flow integrals summed up together to get the total circulation, which is doable. We could definitely do it, but if you look at it, the region in between is this nice square. It's a rectangle. Well, it's a square. And so it would be really easy to do the integral over some rectangular region. So maybe we could use Stokes' theorem, because Stokes' theorem says if you want to find the circulation, you can just actually integrate over the interior. You just have to do the flux of the curl, or del cross f dot n. In this case, things are set up really, really nice. First, we're going to need to have to calculate del cross f. So I, j, and k, and then our del operator, which is d dx, d dy, and d dz, and then our components. Our first component is y squared plus z squared, then x squared plus z squared, and then x squared plus y squared. If we take this determinant, then we get I times the derivative with respect to y would be 2y, minus the derivative with respect to z here would be minus 2z, and then we'd have j times the derivative with respect to z would be 2z, minus the derivative of this with respect to x would be minus 2x here, and then k times 2x minus 2y. Okay, so there is del cross f. Now the normal is the normal that you'd get if you took your right hand, right, and let your fingers naturally curl in this direction. Then with your right hand, you can see your thumb would be poking up that way. So our normal then is going to be straight up out of the plane. So our normal in this case is actually k. So the normal is k. So if we dot this with k, since k is the vector that has components 0, 0, 1, we get 0 times this plus 0 times this plus 1 times that. So curl f dot n is curl f dot k, which is 2x minus 2y. And we just need to integrate around that surface, but the surface is actually a region in the plane, so we can just integrate over the region in the plane. X and y both go from negative 1 to 1. We need to do the curl f dot n, which we found out is 2x minus 2y. And we need to find a conversion factor that will take an area in the region of integration and convert it to an area on the surface. But an area in the region of integration is an area on the surface, because it's just a surface in the xy plane. And so the conversion factor is 1, and then we just get dA, or dx dy, or dy dx. In this case, the bounds make it so it doesn't matter. So rather than having to do 4 flow integrals, we can just do 1 double integral. Antiderivative with respect to y is going to be an integral from negative 1 to 1, but we're going to have to take 2xy minus y squared between negative 1 and 1. And once we do that, then we'll do the integral with respect to x. If I plug in 1 here, I get 2y minus 1. So the integral from negative 1 to 1 of, oh, sorry, I'm plugging that in for x. So I get 2x minus 1. Minus, when I plug in negative 1, I get negative 2x. And again minus 1 dx, and let's see, there's a negative x and a minus 1 would be plus 1, so those cancel. So 2x minus 2x would be 4x, so I just have to integrate from negative 1 to 1, 4x dx, and the antiderivative is 2x squared between negative 1 and 1, but this function has, let's see, we get 2 minus 2, which is 0. So this function has the same value at both 1 and negative 1, so the difference is going to be 0. So there's 0 net circulation around the boundary for this particular vector field. It's easy to find, not by doing 4 flow integrals, summing them up to get the circulation, but just doing one double integral. Didn't have to parameterize any of these segments. Things went really smoothly.